Hello, my name is Naomi Pineda, and I will be talking about how to use active learning in a classroom to introduce students to the topic of real gases and the first law of thermodynamics. So, the objectives of this presentation include the following: define what is active learning, identify examples of active learning activities, identify three resources for active learning activities, go over an example of active learning, identify three differences between real and ideal gases, differentiate heat from work, and finally define the first law of thermodynamics. First, let's start with what active learning is. It is a little different from the traditional way in which lectures are given. So instead of the instructor giving lectures throughout the entire class, students can work together as a team to come up with their own individual conclusions. In active learning, the instructor has more of a role as a facilitator. This way, students are more engaged in the class and enhances student learning because the class is more interesting. This does not also teach them about a specific topic, but it also prepares them for the future because they become better at teamwork, doing their own research, and coming up with their own conclusions. This is not only valuable if they decide to go to grad school, but it also prepares them for their professional lives. They will always have to collaborate with others and must look for information for their future projects. Therefore, active learning does not just enhance learning, but it also equips students with the tools that they will need for their professional lives. Now that we know what active learning is and how we can improve the learning process, let's see how we can use it. With active learning, you can use from a simple activity that lasts a couple minutes, such as writing a one-sentence summary, to a very complex activity such as a jigsaw discussion, which we will talk a little bit more later. First, we need to choose what kind of activity you want to use. Here are some examples from simple to complex activities you can use. So you might want to start the class with a simple activity such as asking questions to test the student's background knowledge. You can also do it on the previous class so you can have a little bit more information before starting the new lecture. Once you know what activity you want to use, explain the activity to the students and what the purpose of the activity is. For example, you tell them you will ask background questions so you can have a better understanding of where the class is, and if you need to go over certain concepts before jumping into a more complex concept. Once you get the results from the activity, you can organize the results for yourself and put them into different groups and modify the teaching plan accordingly. You can pick different activities for a class. This is an example of how you can use active learning. So you can gather information from a previous activity that was given before the class started, such as the background questions that we talked about earlier. This way you know what concepts need to be clarified before advancing with the lecture. So after you organize whatever the questions you think they might need more clarification, you can start the class with that. So after that, you can start the actual lecture of like a 10 to 12 minute lecture and then do a 3 to 4 minute activity such as a fishbowl activity. This is where questions about the lecture will be given to small groups for them to discuss them. After that activity, you can proceed to another 10 to 12 minute lecture and an activity such as a one sentence summary of what they learned. After that, another 10 to 12 minute lecture, and at the end of the class, you can give a 5 to 6 minute summary. This is just an example. Some activities might take longer than others, so you might have to adjust the times accordingly. Some examples of simple activities you can use include the background knowledge probe and one sentence summary. Background knowledge probe is a series of questions asked to the students before the class starts. This helps the instructor determine how much previous knowledge the students have and if the instructor needs to cover some concepts before moving forward. The one sentence summary involves the students summarizing what was taught in class in a single sentence. This way, the students are able to take away the most important concepts from the lecture. One example of a more complex activity is a jigsaw puzzle. In this activity, the class is divided into 4 teams, just as we can see Team Purple, Team Pink, Team Blue, and Team Green. And then they will be given a specific topic which they will have to discuss. This can also be an assignment. Once the teams have discussed their topics, a person from team 1, 2, 3, and 4 will go to form Group A. And then another person from team 1, 2, 3, and 4 will go and form Group B, and so on until you get Group C and Group D. Once the groups are formed, each student will present their group to the group members what they discussed about it with their teams. This way, students will become better at analyzing and presenting information. Now that we know how to use active learning and went over some examples, we will now look at some resources that are available for instructors to look for activities. POGIL stands for Process Oriented Guided Inquiry Learning. It offers a variety of instruction plans in their websites with activities in which students follow the activities and learn from them. In these activities, the role of the instructor is as a facilitator. We also have ADSL, which stands for the Analytical Sciences Digital Library. In their website, there is an option that says Active Learning. There you will find classroom and lab activities that are focused on analytical chemistry. Here you can find a lot of free activities focused on the specific topic that you're teaching, such as equilibrium chemistry and spectroscopic methods. Under Teaching Resources from the University of Minnesota website, you will find a section for active learning as well. There are 2 links in which they provide different simple and complex activities that you can use in the classroom with their description, what to do with the data that you gather from those activities, and the level of preparation needed to complete them. Now there's an example of how to use active learning in a classroom. In this example, I will be going over the topic of real gases and the first law of thermodynamics. At the end of the previous class, you could ask some background questions for the next lecture. You can use clickers or any other app that allows you to ask questions and for students to answer them anonymously and to be able to see the results on a screen in front of the classroom. There are 2 ways where students can use their phones and can participate using a code. Some examples of background questions for this topic would include: in an ideal gas, what makes up for the pressure of a mixture? Do you believe that Dalton's law of partial pressures would apply to real gases? When 2 particles in an ideal gas collide with each other, what kind of collisions do they have? These questions will test their previous knowledge of ideal gases. If, for example, students are having problems understanding what makes a gas ideal, then you might have to go spend a little more time reviewing ideal gases. During the first 10 to 12 minutes of the class, there would be a comparison between ideal and real gases. Ideal gases follow the kinetic molecular theory, which states that particles do not attract or repel, that the volume of each particle is negligible, that molecules are in constant random motion, that collisions between particles are elastic, meaning they do not lose energy when they collide, and that all gases have the same average kinetic energy at a given temperature. The equation for real gases is represented with the equation PV is equal to nRT, where P stands for pressure, V is the total volume, N is the total number of moles, R is a constant, and T is the temperature. In ideal gases, we can also apply Dalton's law of partial pressures, where the sum of the partial pressures is equal to the total pressure. On the other hand, real gases do not follow the kinetic molecular theory assumptions. In real gases, the particles do have volume, there is energy lost in collisions, and there are intermolecular interactions between particles. There are two types of intermolecular interactions, attraction and repulsion. Real gases are represented with the van der Waals equation, where B accounts for the role of repulsion and A accounts for the role of attraction. Now, under what conditions do gases behave ideally? When the temperatures are high and the pressure is low. Gases are ideal at high temperatures because the particles move less at higher temperatures. Therefore, they are further apart from each other and there would be less intermolecular attractions. If there is high pressure, the empty space between molecules is less, and so it becomes harder to assume that volume of the particles is negligible. Now, after going over ideal versus real gases, students would be asked to summarize what they learned in the last 10 to 12 minutes of lecture. They will be told that the purpose of this activity is to see where the class is standing and if there are some concepts that the class might have to go over again. This enables students to focus on the key words and phrases of the lecture that are worth remembering. After the students are done writing their one-sentence summary, a 10 to 12-minute lecture on work will proceed. Work is defined as a motion over some distance against an opposing force. For example, if we have a gas in a cylinder and we apply pressure to that gas using a piston as it is shown in the picture, it would be work. If we apply pressure to the system, in this case the gas, then the sign would be positive because work is being done on the system. But if the system pushes the piston up, then the work is done by the system and therefore the sign would be negative. In order to have work, it requires force and displacement. Heat is energy that moves from a hot object to a cold object, like we can see in this diagram. When the heat is evolved by the system, the heat sign is negative. But if the heat is absorbed by the system, then the sign is positive. Heat requires temperature difference. So in summary, heat is a transfer of thermal energy between two systems, while work is a transfer of mechanical energy between two systems. After giving a lecture differentiating heat from work, students will be asked to create a Venn diagram where they will be asked to put the differences and similarities between the two. They will be told that the purpose of this activity is to visualize the differences and similarities between heat and work. For example, a difference is that heat is a transfer of thermal energy, while work is a transfer of mechanical energy. And in the middle, as a similarity, it can be that both include a transfer of some sort of energy. After completing the Venn diagram, we can move forward with the lecture and go over the first law of thermodynamics. The first law of thermodynamics states that heat is a form of energy, and thermodynamic processes are therefore subject to the principle of conservation of energy. This means that heat energy cannot be created or destroyed. It can, however, be transferred from one location to another and converted to and from other forms of energy. The formula for this is the change in the internal energy is equal to the heat added to the system minus work done by the system. Now that the lecture is over, we can move ahead with a summary of what we went over in class. For example, the main difference between real gases and ideal gases is that ideal gases follow the kinetic molecular energy, while the real gases do not. There are no ideal gases, but there are gases that can behave ideally under low pressure and high temperatures. Heat and work are both a transfer of energy between two systems, but heat is thermal energy while work is mechanical energy. Finally, the first law of thermodynamics states that the change in the internal energy is equal to the heat added to the system minus the work done by the system. This would conclude the lecture. Now that the lecture has concluded, the next class period, a jigsaw activity can be given. For example, you can create 4 different teams using a deck of cards You can give a random card to each student, and they will be asked to get together with their matching symbols. For example, people who have hearts in their cards will form one team. People who have a diamond card will form another team, and so on. The spades team will be given the discussion question regarding real gases. For example, explain the repulsion and attraction intermolecular forces between particles in real gases and how they are included in the van der Waals equation. The heart teams will be given a discussion question regarding ideal gases. For example, under what conditions will a gas most closely follow ideal behavior? Explain why. For the diamonds team, a discussion question about heat will be given. For example, provide a molecular interpretation of heat. How is it different from the equivalent molecular interpretation of work? The clubs team will be given a discussion about work. For example, explain the difference between expansion work against a constant pressure and work of reversible expansion and their consequences. The teams will be given 20 minutes to discuss among themselves. After that, each person from each team will go and form a group, and they will be presenting whatever they discussed in their teams to a group, and each member in each group will be expected to do the same presentation to their other group members. Okay, so this concludes my presentation, and here is a list of my references. Thank you so much for listening.